Hi, this is Dr. Hayek and this video is about acid-base equilibria. In today's topic we will discuss the titration and pH curve of a weak acid and strong base titration. So let me remind you of the outline of this chapter where I will be talking about many different topics. So please refer to the corresponding video for the topic of interest. Now, the titration and pH curve of a weak acid and strong base, it's slightly different than the titration and pH curve of a strong acid and strong base. Now, calculating the pH curve for a weak acid strong base titration involves a two-step procedure. The first one is a stoichiometry problem where the reaction of OH- with a weak acid is assumed to run to completion, and the concentrations of the acid remaining and the conjugate base formed are determined. So as you can see, you have the HA plus OH- will give A- plus H2O. Now the second step is an equilibrium problem. The position of the weak acid equilibrium is determined and the pH is calculated. So now we will determine the pH from the concentration of H+ that's resulting from the dissociation of the acid HA. So let's discuss the following example now, where we have a weak acid, that is the acetic acid, titrated by a strong base, which is the NaOH. So consider the titration of 50 milliliter of 0.1 molar acetic acid, where the Ka is given, with a 0.1 molar sodium hydroxide. The pH will be calculated at various points representing volumes of sodium hydroxide added. And also the pH will be plotted on the graph at your right here. So now, when no sodium hydroxide is added, now we can find the pH of this solution by looking at the equilibrium of the dissociation of the acetic acid. Now, as you know, acetic acid is a weak acid and it will dissociate partially. So the major species are the acetic acid itself and water. Now, the dissociation of acetic acid will result into H+ and acetate. So initially, we had 0.1 molar of acetic acid, 0 molar of H+, and 0 molar of acetate. When X molar of acetic acid will dissociate, it will give X molar of H+ and X molar of acetate. So the equilibrium concentrations are 0.1 minus X molar of acetic acid, X molar of H+ and X molar of acetate. Now plug in these equilibrium concentrations in the expression of Ka and simplify it, since X will be too small compared to 0.1, and when we solve for X we find that X is equal to 1.34 times 10 to the power minus 3 molar, and the pH is equal to 2.87. So this is the initial pH of the solution. We will plug it on the graph. So here's our initial pH, 2.87. Now what happens when we add 10 milliliter of sodium hydroxide? So now the major species are the acetic acid and hydroxide, sodium ion, and water. Now first I will have to deal with the stoichiometry problem, where I will have to assume that the reaction between the acetic acid and the OH- is complete, and therefore I can look at the number of mole before, where I have 5 millimole of acetic acid, and again this is calculated from the molarity multiplied by volume. In a similar way, I can calculate the number of mole of OH-, which is 1.0 millimole, and I have 0 millimole of the acetate before any dissociation of the acetic acid. Now, since the ratio is 1:1 between acetic acid and hydroxide, so I can simply say that the hydroxide is the limiting reactant and it will be completely consumed after reaction. So now the number of mole of hydroxide is equal to 0. However, the number of mole of acetic acid is equal to 4 millimole, and the number of mole of acetate is equal to 1 millimole. So now I can calculate the concentrations of acetic acid and acetate, and these will be the initial concentrations that I will be using in the equilibrium problem. So now if I write the equilibrium, and initially I use the initial concentrations that I found earlier, so I have 6.67 times 10 to the power minus 2 molar of acetic acid and 1.67 times 10 to the power minus 2 molar of acetate. Now when X molar of the acetic acid will dissociate, I will get X molar of H plus and X molar of acetate. So the equilibrium concentrations will be 6.67 times 10 to the power minus 2 minus X for acetic acid, X molar for H plus, and 1.67 times 10 to the power minus 2 plus X for acetate. Plug in these concentrations in the expression of Ka, solving for X, we will find that X is equal to 7.2 times 10 to the power minus 5 molar, and that the pH has increased and it's now 4.14. So we can again plug this on the graph, so we can see there is an increase in the pH. This is normal because we are adding a strong base. Now, what happens if we add 25 milliliter of sodium hydroxide? So again, looking at the major species, I will have the acetic acid, the acetate, the sodium hydroxide, ions, and water. Now, looking at the stoichiometry, the number of mole of OH minus now, it's more than before, so it's 2.5 millimole, and the number of mole of acetic acid is still the same, 5 millimole. Now again, the hydroxide is the limiting reactant, and it will be completely consumed, and the remaining acetic acid is equal to 2.5 millimole, and now I formed more acetate, so I have 2.5 millimole of acetate as well. I can find the concentrations of acetic acid and acetate, and I will use them again in the equilibrium problem as my initial concentrations. Now, in a similar way, when X molar of the acetic acid will dissociate, I will end up having at the equilibrium the concentration of acetic acid is 3.33 times 10 to the power minus 2 minus X. The concentration of H plus is equal to X, and the concentration of acetate is equal to 3.33 times 10 to the power minus 2 plus X molar. Now you can notice something here is that the initial concentrations of acetic acid and of acetate are equal. So in this case, when I calculate the concentration of H plus, I'll find it to be equal to 1.8 times 10 to the power minus 5 molar. Now, when I calculate the pH is equal to 4.74, which is equal to the pKa. Now, this is a very important point in the titration of weak acid by a strong base. Now, this is where half of the acid was consumed, and this point is called half equivalence point, and the pH in this case will be equal to the pKa. Now, if we add more sodium hydroxide, we add 50 milliliter. Now, in this case, the pH will be determined by the acetate. Now, the major species are the acetate, hydroxide, sodium ion, and water. Now, why is that? Let's take a look on the stoichiometry. Before the reaction, we had 5 millimole of acetic acid, and now after adding 50 milliliter of the sodium hydroxide, we will also have 5 millimole of hydroxide. Now, since there's no limiting reactant nor excess, or they are both limiting reactant, so the number of mole of acetic acid and sodium hydroxide will be equal to 0, and the number of mole of acetate will be equal to 5 millimole. So now the only species that I have as a base or acid is the acetate, and it's a base. Now the concentration of acetic acid, we said, is going to be equal to 0, and the concentration of acetate is going to be equal to 5.0 times 10 to the power minus 2 molar. What is going to happen in this case? There is no more acetic acid that will dissociate, so the equilibrium problem will be different now. It's going to be the reaction of the acetate with water that's going to form the acetic acid plus OH minus. Now the pH will be determined from the concentration of the OH minus, again using the autoionization equilibrium constant Kw of water. So initially I had 5.0 times 10 to the power minus 2 molar of acetate and 0 molar of acetic acid and 0 molar of OH minus. Now, when X molar of acetate react with water, it will form X molar of acetic acid and X molar of OH minus. Now at equilibrium, I will have 5.0 times 10 to the power minus 2 molar minus X for acetate, X molar for acetic acid, and X molar for OH minus. Now I cannot use Ka anymore, I have to use Kb, where Kb is found the same way as Ka, is equal to the concentration of acetic acid multiplied by the concentration of OH minus divided by the concentration of acetate. Now the Kb in this case is equal to Kw divided by Ka, and it's equal to 5.6 times 10 to the power minus 10. Now, replacing the equilibrium concentrations in the expression of Kb and solving for X, we find that X is equal to 5.3 times 10 to the power minus 6 molar. Now X in this case is the concentration of OH minus, so we can use Kw to determine the concentration of H plus and therefore determine the pH. We can find that the pH is equal to 8.72. Now this pH is called the equivalence point pH. Now this is the first difference between the weak acid strong base titration and strong acid strong base titration, because the pH at the equivalence point for the strong acid strong base titration, it was equal to 7. However, for the weak acid strong base titration, the pH is equal to 8.72, which means it's higher than 7. Now we can add this point to the graph, so we can see that we started to have an idea about the shape of the pH curve. Now if we add more sodium hydroxide, we add 60 milliliter of sodium hydroxide. Now as you can see that the pH will be determined by the OH minus, since all the acetic acid will be consumed from this reaction and the OH minus is in excess. And now since OH minus is a stronger base than the acetate, now the pH will be determined by the OH minus and by the concentration of OH minus. So now you can see that the concentration of OH minus is equal to 9.1 times 10 to the power minus 3 molar. So now from the concentration of OH minus we can get the concentration of H plus and therefore determine the pH. The pH now is equal to 11.96, and we can add this point to the graph here. So now that we have done the titration and we crossed the equivalence point, and we can plot the curve and we can find the following shape. Now the shape is different than the shape of the pH curve of a strong acid strong base, and there are two main differences between the pH curves of a strong acid strong base and weak acid strong base. So if you plot these two curves, we can see that the first difference is that the starting pH of a strong acid, it's lower than the starting pH of a weak acid. The second difference is that we can see that the pH changes slightly in the case of strong acid. However, we can see that there is a rapid increase at the beginning of the blue curve, which is the weak acid strong base titration. A third difference is that the equivalence point of a strong acid strong base titration, it's at pH equal to 7. However, the equivalence point pH for a weak acid strong base, it's going to be higher than 7. Now one important note is that both curves, they end up the same way, so they share the same part after the equivalence points. Now here I will show you a graph that shows curves for a series of hypothetical acids of different Ka values titrated with the same concentrated sodium hydroxide. So as you can see, this would be the strongest, and then we can see that the weaker the acid, the more the shape of the curve will change, and also the higher the pH of the equivalence point. Okay, so as you can see that for strong acids, they will start at lower pH. There's no rapid increase at the beginning for the pH, and the equivalence point pH is around 7. I hope this video is helpful to you, so please like, share, and subscribe, and I'll see you next time.